Good morning to all. This is Dr. V. Srinivasarao, Assistant Professor of Physics, Government Degree College, Uppal. Today we will discuss about the oscillators in which the basic electronics. So, there only we are discussing the unit 8 part. So, this is elective course. So, in this we have to discuss about the introduction part of the oscillators here. So, in previously we have been discussed that here a rectifier. So, the PN junction diode is a rectifier, means here which may be converting a pulsating AC signals into a DC. So, that is a rectifier here, which is related to oscillators here. The oscillator is an electronic circuit, that means a DC may be converted into a pulsating AC. So, that is the basic nature of the oscillators here. So, this is also an electronic circuit which is going to be generating a periodic wave function, that means where the output without an external signal source. So, it is used to convert, simply you can say that DC to AC, whereas in the case of AC to DC, rectifier. Here converting a DC signal DC to AC, that means that is either voltage or current, whatever it may be here. So, oscillators are circuits that may produce a continuous signal of some type without need of any input. So, here the signal serves as a variety of purpose here, in the case of communication systems, digital systems and test equipment, and there only we are using these oscillators. What do you mean by oscillation? An effect that repeatedly which can takes place and regularly fluctuates about the mean value, and oscillator is circuit that may produce oscillations. So, what are the characteristics of these oscillators? Means here which can have a wave shape, frequency, amplitude, distortion and stability. So, oscillators are circuits which may produce the periodic signals here. So, which may converting a DC power into a AC signal. That means you need to observe that here a repetitive ramp waveform here. You can easily observe from the figure, you can identify that how repeatedly within the same period of time interval, you can able to observe how it is going to be generating. Next is that which repetitive signal is going to be generating and from a DC voltage. So, that here the feedback oscillators, so which relies on a positive feedback of the output, which has to maintain such a oscillations here, and the relaxation oscillators make use of the RC timing, that means resistor capacitor timing circuit, which is going to be generating a non-sinusoidal signal as a square wave. You can easily see that here an oscillator which is having a input as well as the output. From the figure only you can easily observe that DC input signal, input voltage is going to be giving, and oscillator which may converts here a periodic waveform, that means at output section you can have either a sine wave or a square wave or a sawtooth wave, whatever it may be here. Okay. Next is the introduction part of the feedback here. That means the feedback which may gives out the here a portion of the output signal which may back into the input circuit, then you have to say that that is in feedback. So, the result which is in dependence between the output and input of an effective control can be obtained by the working of this circuit. So, here from this circuit you can easily observe that here there are two circuits are there. One is the amplifier with gain, another one is the feedback circuit. So, that here at input stage which may have input voltage for amplifier with gain, and which can have output voltage. So, that what is the gain of this amplifier means the ratio of the output voltage to the input voltage, that is AV, which is a gain of the amplifier, which is nothing but a here AV naught by Vi. But the thing is that here a signal voltage is also there from the figure Vs. So, and a feedback circuit. So, that is the feedback circuit is a beta here. So, the output voltage, a fraction of the output voltage which may be fed through the feedback circuit and which is connected to the input signal. So, you can easily observe that what is the feedback voltage means beta into V naught. So, that is the case. So, there are two types of feedbacks, one is the positive, another one is the negative feedback. So, you can easily observe that here how the strength of the signal which is going to be enhancing, how the strength of the signal which is going to be here going down. That means, here you can easily observe from these two figures, that means output voltage which is giving to the here either inverting or non-inverting. So, you may be observing that here the signal voltage is going to be changing here, increasing or decreasing depending upon the here beta value. So, here the other one is the negative or degenerative feedback. So, in this degenerative feedback is the energy, that means here either voltage or current which is out of the phase and with the input signal. So, that which is going to be opposing it, and the negative feedback which is reduces the gain of the amplifier here. Okay. So, that it is also reduces the distortion, noise, instability, and this feedback which may increases the bandwidth and improves input as well as the output impedances. So, due to these advantages, the negative feedback is frequently used in amplifiers. So, you can see here the negative feedback circuit. Here to input signal you may have 180 degrees out of phase with the input voltage. So, here it is also going to be introducing a 180 degrees of phase at the amplifier, and here the 0 degrees phase shift which is going to be introducing at the feedback network circuit. So, that is the case here, and next one is the positive or regenerative feedback. So, in this the feedback energy here voltage or current which is in phase with the input signal, and the feedback increases the gain of the amplifier and also increases the distortion, noise and instability. Because of these disadvantages, the positive feedback is seldomly employed in amplifiers. So, but positive feedback which is used in oscillators also. So, here also how the input signal which is in phase, or here amplifier is going to be how much phase is there, 180 degrees you may be observing here, and feedback circuit is also going to be having 180 degrees of phase shift here. Okay. So, in these figures here, if you want to calculate the what is the gain of this feedback amplifier means here, which is representing here capital A, and the gain of the amplifier, you know that the ratio of the output voltage to the input voltage is nothing but here gain, and the feedback networks which is going to be extracting a voltage, that is Vf equals to beta into V naught from the output voltage. So, if it is going to be subtracted for a negative feedback, and the signal voltage which may gives you here input voltage equals to signal voltage plus Vf, that is Vf value is beta into V naught. So, here the beta value which is nothing but a ratio of the signal feedback voltage to the output voltage is called here feedback fraction. So, which may be implied to the gain of the amplifier. So, that you can easily follow that here the equation part which may gives out here the ratio of the output voltage to the signal voltage is A into 1 minus A beta. What do you mean by A? Means A is the gain of the amplifier, beta is the fraction of the feedback circuit here, gain of the feedback circuit. So, that here the gain of the amplifier with the feedback which may gives out here AF equals to A by 1 minus A beta. Okay. So, if you are going to be comparing with these positive as well as the negative feedbacks, you can find out that for a negative feedback is the feedback energy is out of phase with their input signal, whereas in the case of positive feedback the phase with there is a energy which is in phase with the input signal, and the gain of the amplifier which is going to be decreasing in the case of negative, for a positive is increasing, stability is also increases, positive is decreasing, noise and distortion decreases, and for positive is increases. And here one thing is that increases the bandwidth and used in amplifiers in negative feedback, whereas in the case of positive feedback, which is used in only in oscillators. Okay. So, what is the main important is that Barkhasen criteria. That means, when this is going to be works as an oscillator, means here if it is going to be fulfilling this condition, that means A beta equals to 1, then the magnitude of the loop gain, which is A beta 1, and the phase shift over the loop is 0 degrees or 360 degrees, and the frequency of the noise in amplifier for which this criteria is going to be satisfied, and then this is the frequency of the oscillations. And the next one is that RC phase shift oscillator. Okay. So, here you can see that here 3 RC combinations are there, and here each RC which is going to be generating 60 degrees of phase, and due to the feedback circuit which is 180, and 3 RC phase is 60 plus 60 plus 60 is 180. So, that total is 0 degrees or 360 degrees. So, like that you have to understand this concept here. The RC phase shift oscillator, which is also called as phase shift oscillator, and which is producing here a sine wave output. If you are going to be observing the output voltage there, here the signal which is a regenerative feedback. Okay. So, and the RC combination which is using here due to this the ability of the capacitor to store an electric charge, and also which is similar to the inductor capacitance LC tank circuit we are using here. So, just now we already discussed that how the phase is going to be here generating with this one RC combination is 60 degrees, other is another 60, third one is the another 60, total is 60, 120, 180 degrees, 3 RC combinations, and due to the feedback is also 180 degrees. By adding these two, 180 plus 180 is 360 degrees. So, like that it can produce a leading phase shift or interchange to produce lagging phase shift. So, which can outcome is that here the same as sine wave oscillations only occurs at the frequency at which overall phase is 360 degrees, or else you need to say that 0 degrees. So, the phase shift oscillator which can utilize the 3 RC circuits which may produce and which may provide 180 degrees phase shift, and when it is going to be coupled with each other 180 degrees of the operational amplifier op amp itself, it is providing necessary feedback to sustain oscillations. So, by varying one or more RC combinations of the phase shift network, the frequency which can be varied, and generally this is done using the 3 ganged variable capacitors. So, here the frequency of the resonant circuit which may gives out here 1 by 2 pi RC into root 2n, whereas the F is the output frequency which measures in hertz, and resistance is ohms, and C is the capacitor in farads, N is the number of RC stages. Okay. So, the gain must be at least to maintain these oscillations. And what are the types of the oscillators? There are many types of the oscillators which can be classified into 2 main categories. One is the harmonic oscillator, then this is known as a linear oscillator, another one is the relaxation oscillator. So, you need to know that here what you mean by harmonic oscillator means the energy flow is always from the active components and to the passive components, and the frequency of the oscillator is decided by the feedback path. Whereas, in the case of relaxation oscillators, here the energy which is exchanged between the active and passive components, and the frequency of the oscillator which is determined by charging and discharging time constants which is involved in this process. So, this harmonic oscillator which may produce low distorted sine wave outputs, while the relaxation oscillator which may generate non-sinusoidal, that means whether it is a sawtooth wave, triangular wave or square waveforms. So, the main types of the oscillators here is RC oscillators which may comes under the Wien bridge oscillator or RC phase shift oscillator, and LC oscillators is the inductor capacitor oscillators, that is here Hartley oscillator, Colpitt's oscillator, Clap oscillator, and third one is the crystal oscillator. So, here what do you mean by Wien bridge oscillators? So, which is a low frequency oscillator. So, the range is from a few kilohertz to 1 megahertz, mega means 10 power 6. So, the Wien bridge oscillator which is a type of phase shift oscillator. So, which is based upon the Wien bridge network comparing 4 arms which is connected in a bridge fashion. So, that in previous case I think so we have been already know that a bridge rectifier. So, there is a half wave rectifier, there is a full wave rectifier, and bridge rectifier we are using 4 diodes. So, similar to that here a 4 arms which are connected in a bridge fashion. So, here 2 arms purely resistive and other 2 arms which are a combination of the R and C, that means a resistor and capacitor. So, one arm has R1 C1 which is connected in series, while R2 C2 which is connected in parallel. So, this is indicating that the 2 arms of the networks behaves identical to that the high pass filter or low pass filter. So, you can able to observe that here R1 C1 and as well as the here R2 C2, okay, and R3 R4 is also there. So, that how many resistors are there? 4 resistors and 2 capacitors. So, this is a bridge network. So, and the 2 arms of the Wien bridge network here you can see here R2 C2 combination as well as the R1 C1 combination. Input signal is there, the output signal is there, and whereas a high pass filter the signal feeding through the R and C, R1 C1, and next one is the which is connected here in a parallel, that means R2 C2 which is a low pass filter. So, in this circuit at higher frequencies the reactance of the capacitors C1 C2 which is must less due to this voltage, and V0 will become 0, R2 will be shortlisted. So, like that here the Wien bridge network makes a lead lag circuit in the case of low and high frequencies. Okay. Next, how we are going to calculate the frequency of the Wien bridge oscillator means here these 2 high and low frequencies there should be existing a particular frequency at which the value of the resistance and the capacitance value which is which becomes equal to the other and which may producing the maximum output voltage. So, what is the frequency? Resonant frequency Fr equals to 1 by 2 pi into square root of R1 C1 R2 C2. Okay. So, if R1 equals to R2 equals to R and C1 equals to C2 equals to C, the same equation the equation becomes here Fr equals to 1 by square root of 2 pi RC. Okay. So, here the Wien bridge oscillator if it is going to be using a BJT, okay, bipolar junction transistor. Okay. So, in this case how the oscillator the amplifier selection section will be compromising the 2-stage amplifier by means of the transistors here Q1 as well as the Q2. So, whereas the output of the Q2 which is fed back into the input value of the Q1 via Wien bridge network. So, here it may be giving out that here the Q1 will appear as it is a collector point after being the signal is going to be amplified with a phase shift of 180 degrees. Whereas, if it is going to be feeding at input to the Q2 transistor via C4 the capacitance C4 and which is going to be here amplified and appears with the additional phase of 180 degrees. So, that the total is here 360 degrees which is satisfying that phase shift criteria to obtain sustained oscillations. Okay. So, here while the kind of the op amp based operational amplifier based Wien bridge oscillator which cannot be operated above the 1 megahertz, okay, 10 power 6 frequencies. So, due to the limitations which is imposed on them by their loop gain here. So, Wien bridge oscillator using an op amp. So, that 3 different cases we have been discussed is that here the thing is that one it is going to be using the diodes and the other one which is going to be using the transistor, and other third one if it is going to be using a operational amplifier. So, okay, 3 cases, 3 different cases here. So, here Wien bridge networks are low frequency oscillator which are used to generate audio and sub audio frequencies, ranging is between the 20 hertz to 20 kilohertz. Okay. So, which may provide the stabilized low distortion sinusoidal output over the wide range of frequency which can be selected using decayed resistance boxes. Next is the RC phase shift oscillator. So, RC means resistor and capacitor network which is going to be providing a phase shift by the required feedback signal, and this have an excellent frequency stability and which can be yield a pure sine wave for a wide range of loads here. So, you can see here RC phase shift network. So, input signal, the signal which is feeding through the capacitor, and a resistor is there which is connected in series here. Across the resistor we are taking the output. Okay. So, here RC phase shift oscillator which is formed the cascading 3 RC phases. Okay. So, which is going to be offering a 60 degrees of phase. So, by 3 RC combinations we can get the total 180 degrees, and the feedback circuit is also going to be getting here another 180 degrees here, totally the 360 degrees. Okay. So, the output frequency which may produce from the RC oscillators which can deviate much from the calculated value rather than in the case of inductor capacitor oscillator, LC oscillator, tank circuit you can say that here. Okay. So, which may be used as a local oscillator for synchronous receivers, musical instruments, and low which can be used as audio frequency generators. Next is the LC oscillators. So, which here which can used in transistors and LC tuned tank circuits, or crystals in their feedback network for hundreds of kilohertz to hundreds of megahertz frequency range, whereas in the case of Wien bridge and RC case is only 10 power 6 kilohertz to 1 megahertz of frequency range, but whereas here hundreds of kilohertz to hundreds of megahertz frequency range we can able to use these LC oscillators. So, what are the examples for this frequency range means Colpitt's oscillator, Hartley oscillator, crystal oscillator. Okay. So, the comparison which have been given out here, how the impedance matchings are going to be changing with respect to the Hartley Colpitt's collapse oscillator. So, first of all another important one is that Hartley oscillator. So, which is a harmonic oscillator repeatedly which is going to be takes place here. So, which was invented by Ralph Hartley in 1915, and these are the tuned circuit oscillators. So, which may produces the waves in the range of radio frequency, and hence here also referred to as RF oscillators. RF means radio frequency oscillators. So, its frequency oscillations which is going to be deciding by this LC means tank circuit. So, which has a capacitor and which is connected in parallel with these two are connected in serially to the inductors here. So, you can see here R1 RC, R1 R2 RC RA, emitter diode, that is RE. Okay. So, here R1 C1 is there, and at input section here we are taking the output signal at CO, and there is a tank circuit we are using here. So, two inductors are there, L1 and L2, and which is connected in series with the capacitor here. So, that is the tank circuit. So, here what the RC, that means here capacitor resistance and emitter resistance is RE, and which is going to be stabilizing the network, whereas R1 and R2 which may forms the voltage divider for biasing network for the transistor in common emitter configuration, and Ci and Co, that is Ci means input capacitor and Co is the output capacitor, that means output decoupling capacitor, whereas C is the emitter capacitor. So, that which may be, and bypass capacitor is which is used for bypassing the amplified AC signal. Okay. So, here amplified means here strengthen the signal. Whenever a weak signal fed through this here, the signal may be enhanced, that means signal is going to be amplified. So, this amplified AC signal. So, that here L1 and L2 are the two inductors and a capacitor which is a C. So, that may be forming a here a tank circuit. So, here the gain of this circuit which may gives here the ratio of the L1 to the L2, and the frequency of the oscillator which is nothing but here 1 by 2 pi square root of LC. Next, Hartley oscillator. So, here these Hartley oscillators are available in many different configurations. So, which may including series or shunted, common emitter or common base configuration, and bipolar junction transistor BJT or FET means field effective transistor. So, that here if the above figure which is going to be replacing by an amplifier and of any other kind like that inverting amplifier formed by an operational amplifier, that means op amp. So, the gain of this inverting amplifier which may gives that here that is a negative RF by RI. So, that here the gain of the circuit which is less dependent on the circuit element of the tank circuit LC circuit, and this may increases the stability of the oscillators in terms of its frequency range. So, you can easily observe the figure where we are using an operational amplifier. So, that is here the other one is the Hartley oscillator, which are advantageous, they are easy tunable circuit with very few components including capacitors, there are two inductors which are tapped here. So, here this kind of oscillator which is not suitable for lower frequencies and which may result here a large sized inductor which makes the circuit bulky. Okay. So, Colpitt's oscillator which is another type of LC oscillator which may falls under the category of harmonic oscillator, and here the Colpitt's oscillator here there is a feedback network which is made up of a pair of tapped circuits and an inductor L is going to be using here. So, you can able to observe the Colpitt's oscillator also. Okay. So, the frequency is 1 by 2 pi LC square root of LC, the capacitance effective capacitance of the capacitor which may be gives out here C1 C2 by C1 plus C2. So, this ends our lecture. So, that you can have that an idea about that here oscillator, what do you mean by oscillator, what is a feedback oscillator, how many types of oscillators are there, positive and negative feedback, based on that RC phase shift oscillator. Next is the Weinbridge oscillator, Hartley oscillator, Colpitt's oscillator. So, all these are comes under the here how the frequency range, depending upon the frequency range they may be works out here. Okay. Right. Thank you one and all.